All right, time to go teach. All right, welcome to this next episode of Tutors, where we're going to be looking again at biochemistry, and we are going to be looking at our first category of biomacromolecules, which would be lipids, your fats, oils, and your waxes. Let's begin. Here we go. Target of the day, identifying first, is a molecule a lipid or not? So that's going to be our first target of the day. The second one is to be able to describe the different structures of a fatty acid. And again, we're going to have to look at what a fatty acid is too, because you probably are not very well aware of it right yet. And lastly, compare and contrast saturated, transunsaturated, and cis-unsaturated. And if that seems like I'm talking a completely different language, well, that's okay. We'll get there in a couple minutes, and then it hopefully will all be clear. So first off, lipids, what are they? Well, the primary component of a lipid is something called a fatty acid. That is one of the monomers of a lipid. So we need to understand it. Now, the way it works out is it's made up of two parts: a hydrocarbon chain, also referred to as a hydrocarbon tail, and a carboxyl group on one of the ends. What is a carboxyl group? Well, here we go. This is it. This is our carboxyl group right here. This carbon double bonded to an oxygen, single bonded to an oxygen, which is single bonded to a hydrogen. That is a carboxyl group. And then this back part is, again, our hydrocarbon chain or our hydrocarbon tail. Remembering that our hydrocarbon tail is completely nonpolar. But this carboxyl group, well, yes, there's polarity, and we're going to have to look to see how that polarity actually matters as we move on. There is a shortcut way to draw these, and I just want you to be aware of it in case you ever come across it. Here's how it works out. It would look something like this. These two diagrams are showing the exact same thing. This is our carboxyl head, and then this is our hydrocarbon tail. At every single angle, or in other words, where any two lines meet, that is where a carbon exists. So you can see every single angle is a carbon. And because every carbon makes 4 bonds, that means we know that every single one of these carbons has to also make 4 bonds. So we know that this would just be a single carbon because we have 1, 2, 3, 4 bonds. We also know that this would not be a single carbon, it would be a CH2, or a carbon bonded to 2 hydrogens, because we only see 2 bonds, and so the 2 bonds that we don't see, we know have to be to hydrogen. And that works for every single one of our angles until we get to the very last one, which that last carbon, well, it only shows 1 bond. So that means instead of having only 2 bonds to hydrogen, it must have 3 bonds. So that must be a CH3. And so this is our structure that we had previously, but we could show it just with this diagram right here. So that's a shortcut way to draw it, instead of drawing each and every element. We have to identify all the elements that are not carbon or hydrogen, except if hydrogen is bonded to something that is not carbon. So this oxygen, we have to show that it is bonded to a hydrogen. We can't just assume that it's bonded to a hydrogen. Now, fatty acids, they happen to come in 2 different varieties, 2 different types. Those 2 different types are saturated or unsaturated. Saturation is all about how much hydrogen is present in that hydrocarbon tail. If you can't add any more hydrogens, that means that it would be saturated with hydrogen. If you can add more hydrogen, then that would mean it would be unsaturated. What that is actually referring to is double bonds between the carbons. If we were to look at it, these are saturated fatty acids. Each of these carbons is attached to 2 hydrogens until we get to the very last one, which is attached to 3 hydrogens. You can't fit any more hydrogen. It is fully saturated. And because of that, these molecules are able to pack together very tightly. And remember, the tighter they are packed together, the more solid they would be. The less tightly packed, the more fluid they would be, the more liquid they would be. That's going to be important for us as we move on. So saturated fatty acids, they can pack together very tightly and thus be more solids at room temperature. Unsaturated fatty acids come in 2 different varieties, trans or cis. Now, trans unsaturated, how you would know it's a trans unsaturated is because, first off, you'd see a double bond, or you'd see multiple double bonds. But the key is it has to have double bonds. Double bonding means that you have less hydrogens. This carbon right here has 1, 2, 3 bonds. So it can only attach to 1 hydrogen, not 2 like this one can. So, and this carbon can only attach to 1 hydrogen as well, because it also has 1, 2, 3 bonds showing. So it can only attach to 1 hydrogen. So every time that you have double bonding, that means that you are going to be able to have less hydrogens in the hydrocarbon tail. And trans is referring to this bond and this bond. The bond from this carbon and the bond from this carbon. And trans means across. So what we have is this bond is across from this bond. They are not on the same side. They are on opposite sides. This bond is coming off this way, and this bond is coming off the opposite way. So they are what we would call trans unsaturated fats. This would be a trans polyunsaturated fat because it happens to be unsaturated more than one time. Same with this trans fat. But much like saturated fats, trans fats are able to pack together tightly and be more solid. They don't have a great amount of fluidity because they are able to pack together very tightly, because even with the trans bonding, they have pretty much a straight chain that can get nice and packed together. This is very different from cis unsaturated fats, where cis unsaturated fats, because of the double bond, it makes kinks in that tail. The tail doesn't just go in about a straight line, it actually curves. These fatty acids are unable to get really tightly packed, and so they stay more fluid. They don't end up being very solid. They typically are liquids at room temperature, for example. Hello again. Just wanted to take another second out of our regular video just to explain a little bit about the concepts that we're just going over. When we're talking about single bonds versus double bonds, it's extremely important that we understand what effect that actually has. So, when we have single bonds, that allows for freedom of rotation. The atoms that are bonded around each other, they can continue to rotate around that single bond. But when you have a double bond, that means that you don't have freedom of rotation. These are fixed in this orientation. So this atom cannot rotate around this bond. This atom also cannot rotate around this bond. That means that we are fixed in this conformation. This is how a saturated fatty acid will look. The hydrocarbons are able to rotate around each other because they are full of only single bonds. On the other hand, unsaturated fatty acids have a double bond, at least one, within their hydrocarbon tail. And that means that there is going to be a rigidity there where they cannot rotate around. The way that it works out is there are 2 different categories. This happens to be a trans unsaturated fat. It's trans because the substitutions or the bonds, go across from each other. So this carbon is bonded to another carbon in the exact opposite direction as this carbon is bonded to this carbon. And since we can't rotate around, that means that these two carbons will always be facing in opposite directions, and they are across from each other, which is why we call it trans. If we were to take this carbon off and bond it to this opposite bond, now we would be on the same side, which is the cis conformation. So this is cis because cis means same. So that's what's going on when we're looking at cis unsaturated fats, or when we're looking at trans unsaturated fats. Another important thing to recognize is that trans unsaturated fats, they look very similar in their shape and structure to saturated fats, following very similar angles. Whereas cis unsaturated fats, they do not follow the same angle pattern. They have a little bend in them, which means that they cannot get as close or as tightly packed as the saturated fats or as the trans fats. And now, back to your regular lesson. So here, what you see is, again, we have our double bond between these two different carbons. So we have our double bond right here between this carbon and this carbon. And that means that this carbon only is attached to one other hydrogen, and this carbon is only attached to one other hydrogen. But the important aspect for why it's a cis unsaturated fat is because this bond and this bond go off in the same direction. Cis means same. And since these bonds go off in the same direction, that means that you are going to end up with a slight kink or a slight bend in the hydrocarbon tail. If it's cis polyunsaturated, that means that you could end up with multiple kinks in that tail. Compare again to a trans, which goes in a pretty much straight line. So this, again, this is our trans polyunsaturated, and you see how this bond is across from this bond, and you see how this bond and this bond are on the same side. So both these bonds going in the same direction compared to both of these bonds going in opposite directions. So this is a cis unsaturated, and this is a trans unsaturated. Trans unsaturated are able to pack tightly together. Cis unsaturated, you can see, are unable to pack tightly together because of that kinking that occurs because of those double bonds. So saturated fats and trans unsaturated fats, they pack tightly together, and they are more likely to be solid. This also is important for us when we talk about diet, because that also means that they're more likely to be solid in, say, your blood vessels, which is something that we don't like. Cis unsaturated fats are less able to pack tightly together. These are like your vegetable oil, where they are more likely to be liquid and thus have more fluidity because they can't pack together. So in summary of all that, lipids, they're composed mostly of carbon and hydrogen, vast amounts of carbon and hydrogen, which gives them pretty much a nonpolar character. There is a tiniest bit of polarity, but for the most part, they are nonpolar. And the presence of double bonds in the hydrocarbon tail determines on whether or not that fatty acid is saturated or unsaturated. If it has no double bonding, that means it is saturated. If it has double bonding, that means it's unsaturated, either cis or trans unsaturated. If it is a trans unsaturated fat, then it has much more characteristics of a saturated fat, where it's more likely to be a solid than a cis unsaturated fat, which is more likely to be a liquid. That's it for this time. Be awesome. Stay awesome.